All right. So again, this is the document that we're working off of, and talks about what we're trying to identify, looking up what a hole is, or removable discontinuity is something that we want to take care of, but we want to know about in behavior of the rational functions. The end goal really is to be able to sketch a graph of a rational function if we see the rational function. Okay. They will sometimes have high and low points. That's not something that Algebra 2 equips you to find very well, so we're not going to worry about finding those. So our strategy to get a hold of this is to use Desmos and graph a variety of different rational functions and see what we notice. Okay, and there's kind of a list here that I'll pop back to every once in a while, but I've preloaded Desmos here a little bit to make this a little more efficient. So from the beginning here, even something like y equals x minus 2 is still technically a rational function because the denominator just happens to be 1. And we notice that the features that it has that we can identify are there's an x-intercept and there's a y-intercept that are pretty easy to find. And if we zoom out a little bit, we see this in behavior that says as x goes to negative infinity, the y values are going to negative infinity. And as x goes out here towards positive infinity, the y values are also going toward positive infinity. Okay. We find y-intercepts the same way we always find y-intercepts. Y-intercept is on the y-axis, which means it is 0 comma something. So if we just put a 0 in for the x's in the problem, when we put a 0 in for this x in the x minus 2, we get a 0 minus 2 and says the y-intercept is negative 2. X-intercepts we get by setting the y value equal to 0 because this is something comma 0. And if we put the y value equal to 0, add 2 to both sides in this case because it's a nice easy linear thing and it tells us that it's going to cross there at 2. Okay. So moving on and complicating that a little bit, let's take our x minus 2 and divide it by x minus 1 and see what changes. Now that we have a variable in the denominator, there is the potential that some value of that variable could put a 0 in the denominator, which would make us divide by 0. And the visual representation of dividing by 0 is a vertical asymptote. We can see here that negative 1 would make me divide by 0 if I set x plus 1 equals 0. And I'm going to check that here by putting x equals negative 1, and it draws a line in there that separates those two arms of this graph, or whatever we want to call them, and verifies that's where that is. Okay. Now, what do these have in common? Well, they have the same x-intercept and they have the same y-intercept. Okay. The y-intercept, again, if I put zeros in for the x's, I get 0 minus 2 is negative 2 over 0 plus 1, which is 1. Negative 2 divided by 1 is negative 2. Okay. And it has the same x-intercept here that I had from the x minus 2 in the first place, which makes me believe that maybe the numerator has something to do with x-intercepts. Okay. So let's further complicate. Well, let's talk about the in behavior on this one. If I zoom out on this one, I can see that it appears to be a horizontal asymptote. That's one kind of in behavior. And as I cruise along here, I see that the output values are positive and very close to 1, and out here also positive and very close to 1. Okay. Why that is may take a little bit more searching. We'll see if we can come up with a reason to make it something else. Okay. Take that first one out and complicate a little bit more by putting another piece in the numerator. So our numerator now would be a quadratic because it has two linear terms multiplied together. And what's changed? Well, we had the blue one here. For one thing, obviously the in behavior has changed. It's not flattening out to 1 anymore. Now it looks more like the end behavior of that first one. Okay, it seems to have more the end behavior of just the linear function there. That's interesting. Okay. If we want to look for where the vertical asymptote is, that appears to still be in the same spot as it was before. What the equations have in common is they both still have just an x plus 1 in the denominator. The thing that has changed in the numerator is there's an additional piece up there, and my x-intercepts, if I look at the green function here, I've got an x-intercept at -3, and I still have one at 2, and that 2 doesn't maybe surprise me. It's the same thing. I know that if I put a 2 in here, I get a 0 in the numerator either way, and 0 divided by 3 is 0, so it gives me an output of 0. But now that I have the -3 in there, if I put a -3 in for x, I get a -3 minus 2, which is -5, but that -5 gets multiplied by 0 on this side. And so the numerator comes out 0 again. The denominator is -2, but 0 divided by -2 is 0. So that's why this one has to cross here. If I had taken that extra piece and instead put that extra piece in the denominator, okay, then I get something very different looking from the blue one that we had originally. I do, though, see if I zoom out here, this now has apparently a horizontal asymptote again, but the horizontal asymptote this time is below the x-axis out here, but it's getting closer and closer to 0, not to 1. And on this side, if I get on that graph, I'm getting closer and closer to 0, not to 1, but I'm above the axis now. So it's like it's coming back down toward the x-axis there. If I come in to see what's happened here, I still have the x-intercept at 2. That shouldn't surprise me. I put a 2 in for x, I get a 0 over 3 times 5, 0 over 15 is 0. My y-intercept has changed. If I put a 0 in for the x, I get a -2 over 1 times 3, so that says -2/3, and if I hover over there, I get the decimal equivalent of -2/3. And still, do I still have that vertical asymptote at -1? Looks like it. That does that. But it looks like I have another vertical asymptote now because my graph now appears to be in 3 distinct pieces. And so that other piece, where do we think that is? -3. So let's test that. X equals -3, and that seems to go right into that spot where we expected it to be. Okay. And so the 3 pieces that I have one over here, and notice the behavior around the asymptotes. Okay, when we think back to what the reciprocal function looked like, the reciprocal function came in like this, went down as it approached the vertical asymptote. It had to go down toward -infinity, and on the other side of the asymptote, it was coming down from +infinity. And then we have another vertical asymptote here, and as we approach that asymptote, this is going up to +infinity, and on this side, it's coming up from -infinity as it goes across there. It comes up that way. We know it has to cross at 2. It crosses at 2 and then shoots up above it a little bit. It's hard to see that it went very far, but we know that it goes back down toward 0 on the other end. We don't necessarily know why yet, but we can see that that's what's happening. This behavior around an asymptote of it going to -infinity on one side and +infinity on the other, that's normal asymptote behavior. That's what happens there, and there's ways to explore with numbers and see exactly why it has to happen that way. this piece in the middle here that comes down and then turns around, the main reason that that's, I mean, is it possible that it could get down to hit the x-axis? Well, maybe, but the thing is, we already knew that the only way that this was going to hit the x-axis was if x was 2. It's the only way to make this thing 0, and since 2 is not between those asymptotes, it's not going to cross between those asymptotes. Okay? If we messed around with this a little bit, and let's move our, let's make this a +2. If we make that a +2, then now it does hit the 0 between the asymptotes. Okay? And the end behavior hasn't changed at all. And this came down this way, went to negative infinity on that, was coming down from positive infinity on this side, but this time there was a place for it to cross the x-axis, so it had to go down and cross the x-axis, and then the next thing it's running into is this vertical asymptote, so it has to do its normal asymptote thing on that, and then switches over to the other side, and this time doesn't hit over here, but continues to go down and get closer and closer to 0. Okay? We could put this thing on the other side. If I put this at x plus 4, then now it crosses on this side. Okay? So it hits at -4, and it's coming in from close to 0, has to separate from the axis a little bit so it can come up and cross there, do its normal asymptote thing. This time it comes up and doesn't have a place to cross, so it has to turn and do its normal asymptote thing over there, and then normal asymptote thing over here. Okay? So the positioning of the asymptotes with respect to the zeros does a lot to tell you about what shape the graph has to have in those different places. Okay? Let me turn these asymptotes back off for a second, and I'm going to throw an extra one in here. Let me see, x plus 4 doesn't really pay to communicate those anymore. So here's a new one. Okay. On this one, I've got quadratic in the numerator and quadratic in the denominator. Okay. And if you notice, one of the things that has changed here, I can make this match a little bit closer. Let me move this one back to a 2 and a -3 so that we have some things in common between those. Okay. We see our our last one that was quadratic in the denominator and linear in the numerator, or degree 2 in the denominator, degree 1 in the numerator. That's the purple one that has the horizontal asymptote at 0. Okay. We now have, the black one now has a horizontal asymptote again, and it looks like, if we go out here a ways on that, that it's getting close to 1 again. Okay. We had a previous graph, the last one we had that got close to 1 was this one up here. Okay, that if I turn that one back off, this one was also, when it was a linear divided by a linear, it got close to 1. Now that it's quadratic divided by quadratic, it's getting close to 1. Okay, it's something about the degree comparison between the numerator and the denominator, right? Degree 1 levels off to 1. Degree 1 levels off to 1. This one was degree 2 on the top, degree 1 on the bottom, and it didn't have a horizontal asymptote at all. This one was degree 1 on the top, degree 2 on the bottom, and its horizontal asymptote was at 0. So there's some connections that can be made there. I could also mess around with some stretches here. This was part in the document. If I put a 2 in front of this, then did you see what happened? In fact, this has a nice feature in here. I'm just going to put an A there and add what they call a slider. And as I change my values of A, I can see what happens to the graph. Okay, there's the a of 1 that I had before. What's happening as I increase the value of a?
Horizontal stretch.
Okay. Is it stretching horizontally?
No.
Vertically, right? These points where it crosses the x-axis aren't changing at all. They're staying exactly where they are. But my vertical stretch, if I get this out here to, let me just put it at 4. Okay. And I zoom out here, where is this leveling off to? Can you see the numbers? It's getting very close to 4. It used to level off at 1, but we vertically stretched it by 4. So now it's 4 times as far away from the x-axis as it was before. Okay. The other thing that's changing is the location of the y-intercept, because the y-intercept when we were at 1 here, if we put that in, we get a 4 times negative 1 over 2 times negative 3, so that's a negative 4 over negative 6. That's 2/3. So there's the 2/3, but if I bump this up to 3, 2/3 times 3 is exactly 2. So vertical stretches that part, but this allows me, this is the way that I can make that show up in places where I want it to. Okay. Now, when I crossed over into negative values of a, what happened? It reflects. Okay. And so if I go to -3 for this value, where do you think that horizontal asymptote is now? -3. Okay. I can go down here and I could, like I was doing before, I could say, show me where y equals -3 is, and I can see it right there, matching what we had. Okay.
So to find the horizontal asymptote, would you subtract the degree of the polynomials?
It's not so much subtracting them as it is comparing them to begin with.
Yeah.
Okay, so the comparison, when we had a horizontal asymptote, there's 2 things that gave us horizontal asymptotes, and they're kind of different. One of them was when the degree in the numerator was the same as the degree in the denominator. Okay, then that gave us, it leveled off to some number that wasn't 0. But when the degree in the denominator was bigger than the degree in the numerator, then it leveled off to 0. So that gave us a horizontal asymptote at 0. But if the degree in the numerator is the same as the degree in the denominator, then we start comparing the numbers that are out in front of these. If I put a 2 here, so I now have a -3 over 2, well, the horizontal asymptote is now approaching -3/2. Okay. So if this thing was all multiplied out, if I did the x plus 4 times the x minus 1, it would start with an x squared, right? That would then get multiplied by the a, which is now 3, so I would see a -3x squared plus some other stuff. And in the denominator, I would see a 2x squared plus some other stuff.
So if they have the same degree, you can divide the
leading coefficients, and you will find the horizontal asymptote. Okay. Yep. All right, if we jump back to our list, we tried where there are more factors in the numerator than the denominator. We tried where there's more factors in the denominator than the numerator. We had where the numerator and denominator have the same number of factors. We haven't repeated a factor in the numerator. Let's take a look at what that looks like. So repeating the factor in the numerator, if I went back to this one right here, if I wanted to repeat the x plus 4, I could just square it. That means x plus 4 twice, right? And what happens here? Okay, let me, I'm going to modify one here and take this extra term off. Okay. So the black graph has just x plus 4, and the, I need to zoom in here a little bit so we can see what's happening. Okay. The black graph has just x plus 4. The purple graph is x plus 4 squared. Okay. And so if we look at the black graph, the degree in the denominator is bigger than the numerator. So where is its horizontal asymptote? 0. That one's at 0, and it's down here on the negative side, and it's coming up, and it crosses the x-axis here at 4. Okay, so if we traced along here, negative values there, hits 0, and then crosses to positive values. But the purple graph, as it comes in, is positive values, hits the 0, and then continues on with positive values. Okay? So it touches, but it doesn't cross. Okay? This we would have in the last semester called this a 0 of multiplicity 2. Right? So when the 0 has multiplicity 2, it kind of feels like one of those quadratics that's just been shifted over a little bit. So the way that it interacts with the x-axis is a little bit more like a parabola than a straight line. It touches, but it doesn't cross. Okay. So that is one of the differences that we see in there when we duplicate something in the numerator. Okay. So multiplicity of a 0 makes it just touch and not cross, okay, when it's an even multiplicity. Okay. If I came back, let me compare that to what happens if I'm going to square this one. So let me see if I can duplicate here. Let's put another x plus 3 on this one. And turn that on. So blue graph is x minus 2 times x plus 3 over x minus 1. Okay. Degree in the numerator was bigger than the degree in the denominator, so it had this negative infinity in behavior on the left, and positive infinity in behavior on the right. Okay. But the green graph now is quadratic in the numerator, quadratic in the denominator. Degrees are the same, so it has the horizontal asymptote that's heading out there toward 1. Okay. It crosses the x-axis in exactly the same places. Okay. It has the vertical asymptote, if I can turn that back on, is in exactly the same place, but what's different here? Okay. It doesn't look like normal asymptote behavior, right? Our normal asymptote behavior is positive infinity on one side, negative infinity on the other side. Okay. This is negative infinity on both sides. Okay. And that seemed to have happened because I squared the asymptote. Okay. And so squared asymptotes tend to look a little bit more like a volcano, right? It's kind of a reflected volcano, but it goes to the same thing on both sides. The other way to compare those, if we compared both that one and I already took out my other one, oh, that one. Okay. We had this one where we had a multiplicity in the numerator, and so it came down to the axis, but it didn't cross it. When we had a multiplicity on this vertical asymptote, it was below the x-axis, and on the other side it was still below the x-axis, so it didn't cross to the other side of the x-axis. So it's the other way to think about even multiplicity is it doesn't allow you to move to the opposite side of the axis from where you were. Okay. Normally, if we just have this one up here where these zeros are multiplicity 1, then this one, this graph was above the x-axis here, it hit the 0 and now it's below, it crossed. Okay. This was below and now it's above, it was able to cross. Okay. So that explores a couple of those other things in here, the repeated factors in the numerator and the denominator. We changed the leading coefficients around. That's when we played with that A slider. The only thing that we haven't done is this factors in the numerator are the same as the factors in the denominator. And so if I were to come up here and say, I'm going to work off of this one, I'll turn this off for the moment. And I'm going to put an x minus 3 in the numerator as well. I don't want it in the power though. Okay. So there's, okay, well, does that do what you expected it to do? Okay. What did you think was going to happen?
I thought it would, I didn't think the vertical asymptote would change.
Okay. There used to be 2, right? And now there's only 1. Okay. But there's 2 places that make the numerator 0, so doesn't that kind of say there's two places where it should cross the x-axis? This says there should be 2 vertical asymptotes, but the thing is, we would expect it to cross the x-axis at 3, and we would expect there to be a vertical asymptote at 3. We can't do both of those things, okay? Because 3 definitely makes me divide by 0, and so I can't put a 3 in here. And so it can't make that a 0, but if I get up on this thing, watch what happens as I move out towards 3 here. Everything's behaving normally. Oh, I moved past 3. When I hit 3, did you see it? It says it's undefined there. Okay? If I didn't trace to this, I would never see that that was a problem. Right? I can tell it's a problem from the equation, though. Okay, when you did the domain stuff, if I asked you what's the domain of this rational function, you would have said x can't be -2 and x can't be 3. Okay, even though 3 seemed like it was going to do something for us in the numerator, we can't use it. Okay, if I come down here and I change this, I'm going to change this into an x plus 4 over an x plus 2. So I'm going to get rid of this one. Okay. And if I graph that, but if I trace here to the 3, this takes on a value at 3. If I can hit it. 3 comma 1.4. Okay. If I put a 3 into this version, I get 7/5. Okay, so I can see where the hole was. The fact that the x minus 3 over x minus 3 was here told me there was going to be a hole in the graph there. Okay. I have to cancel them and then put the 3 in to figure out exactly where that hole is. Okay. This is the kind of exploration that you can do. Okay. I've got something that I can hand out to you that will probably help with that a little bit. I'll give it to everybody else probably on Monday to help with that. But for now, that was a plenty long video. We'll see if it even, yep, that was a very long video.